Okay, I'm talking about a solid sphere. Solid sphere. Solid sphere. So if I am taking a solid sphere, say for example, okay, in a solid sphere, what is going to happen is all the charges are present inside as well as outside, and they are static. They don't move, nothing. Okay, they are everywhere. It is a solid sphere. I want to find out, basically, I just want to find out the electric field intensity. I want to find out the electric field intensity at this point, P, due to the solid sphere. What is going to be my Gaussian surface?
A sphere.
Yeah, it's a sphere. Everyone listen, this is not a two-dimensional thing, it's a three-dimensional thing, in case you're wondering. So you have to imagine that the sphere also is going to be, the sphere is also going to be in the form of a, it's going to be a Gaussian surface. Okay. So now if I take a small element over here, if I take a small element over here, then the electric field, see, remember, this is a sphere with all charges which are inside it. So of course it's going to radiate electric field lines like this. Okay, it's going to radiate in every direction, because charges have a property of, okay, emerging or contracting electric field lines. And so now if the electric field line through this small element over here is like this, area vector also will be how? It will be in the same direction. Okay, so essentially what we can say is that theta is going to be 0. Why? Because our Gaussian surface is symmetrical to the shape which we have taken. It's symmetrical to the shape we have taken. Okay, so now what we know, according to Gauss's law, we can directly start it. That is phi is equal to phi total is equal to what? Q in, that is charge enclosed by the surface upon epsilon naught. Okay, charge enclosed by the surface upon epsilon naught. And how we can write phi? The reason I did flux earlier is so that you understand what the full form of phi is. Okay, so like what is it equating to? So it equates to electric field lines into area vector. Am I right? Electric field lines into area vector, which is equal to charge enclosed. Now if I tell you that the entire charge in this sphere is going to be a capital Q, is going to be a capital Q, what is going to be the charge enclosed by it then? The total charge enclosed by the Gaussian sphere is going to be capital Q. Yes or no?
Yes, sir.
Okay. Upon what? Upon epsilon naught. Now tell me, what is the area? Area of the sphere?
4 pi r square.
4
4 pi r square.
So can I take 4 pi r square here, right here? Okay. So I can write
Yes.
that it, I can remove this a and I can write 4 pi r square epsilon naught. How I can write 4 pi epsilon naught as? I can write
Q by
Kq by r square.
epsilon.
kq by r square. Yeah, it is not epsilon. Don't make okay, no problem. Mistakes happen, practice makes us perfect. Okay, even I make mistakes. So anyways, you understood the electric field intensity at this point P due to a sphere. Okay, it is kq by r square, and it is similar to the electric field intensity at a point P due to a hollow sphere as well. Yes or no? We did the same thing, na? We did the same thing. But let us now understand a small change in us in this concept, a slight complexity, that if I am taking a solid sphere, let's say I'm taking a bigger one this time, and I want to find out the electric field intensity at a point which is inside the sphere, considering the fact that this is a solid sphere, so charges are there everywhere. So even if I make a Gaussian surface, what is going to happen? I am going to basically enclose a charge. Is it right or no? Yes or no? Okay.
Yes, sir.
Yeah, the total charge, we can consider the total charge of this sphere to be what? Capital Q. Okay, so I will write Q here, capital Q. Okay, and I will write the radius of it, that is R. Okay, capital Q, radius R. I want to find out the electric field intensity at this point P, which is inside the sphere. What is going to be my Gaussian surface?
Sphere.
It's going to be a
Sphere.
sphere. It's going to be an internal sphere. Okay, so I will just take this point here. I'll keep it here, right here. So at least I'll make a sphere, no? Okay, so that is some kind of a sphere. And now the thing is, electric field intensity will be in which direction? It will still be, if I take a small element inside this, it is still going to be this side. Because why? Why? Because, see, I'll tell you, always remember, electric field lines, they are always projected perpendicular to the surface. Okay, if it is a charge which is kept inside, okay, electric field lines, okay, charge is basically where, consider the charge to be right here at the center. Okay, so electric field lines produced by this will be perpendicular to this entire sphere, and so I can say that through this element also it will be in the x-axis direction, if considering the fact that I'm taking this small element to be in the direction of x. And then what is going to happen is basically the area vector also will be in the direction of x. Okay, so I can write that phi total, I can immediately, once I've drawn the diagram, concept is clear, I can write phi total is equal to q upon epsilon naught, q enclosed upon epsilon naught. Okay, q enclosed upon epsilon naught. What this basically then turns out to be is the same thing which we have done earlier, that is EA equals to what? Qn. What is Qn? What is going to be Qn? Any guesses? See, I'll tell you a small trick. Okay, see, I'll tell you this trick. If suppose you are taking any time you take an element inside any object, say suppose, okay, I'm just sliding off the topic a little bit for you to understand something. If I am taking a sphere and I was trying to find it out through integration method, and I take an element which might be a sphere only, okay, and I'm trying to tell you that I will integrate the sphere at this point and I will integrate the sphere all the way to this r radius. Okay, actually you know that you're doing that integration, but you have to specify that where, you have to specify that you are using a certain element which is basically a sphere and you are doing it inside another sphere. Okay, so that you will define in charge density. Okay, you will say that q, okay, what is it? Lambda is equal to charge per unit volume, suppose, charge per unit volume. And so what you can say is dq is everyone understanding? Dq is equal to lambda dv. So what is lambda here? What is lambda? Lambda is the total charge q upon the volume of the entire sphere. Is everyone understanding? Any doubt, please tell me. I'm trying to make you understand something. If suppose,
Sir,
yeah,
sir, can you please explain this part again?
yeah, definitely. Look here. Okay, now see, okay, look here. We know one thing. We know one thing, that we are taking a Gaussian sphere inside a sphere. Okay, this Gaussian sphere could have been a disk also. This Gaussian sphere could have been anything. We chose to take it as a sphere so that it is easy for our calculation. But you have to, the fact that only you know that you have taken a Gaussian surface over here, which is a sphere, and it is inside it's inside a solid sphere. You have taken a Gaussian sphere inside a sphere. But that is no use only if you know it. You have to mention that in the equations. The equation has to know that you have taken a solid Gaussian sphere inside a solid sphere. You understood this point? This statement you have understood? So I am going to do that. I am exactly going to do that. I am actually going to define, or I am going to specify that I am using a Gaussian sphere, okay, for my ease of calculations. And how am I going to do that? Is basically, see this Q in, okay, charge enclosed. I can write charge Q. Look here, forget this part, just look at the Q. Okay, I can write lambda is equal to Q upon epsilon naught. I can write this or not? Yes or no? I can write it. Sorry, charge per unit area or charge per unit volume. Can I write this?
Yes,
Yes,
sir.
sir.
So I can write this. So then I can also write that Q is equal to lambda into V. I just took V there. Okay. So now I can write that dQ is equal to lambda dV. Okay, dQ is equal to lambda dV. Now see how I am specifying that I am using a Gaussian surface, which is a sphere inside of a solid sphere. This is how I am going to do it. So I am going to write that dQ is equal to charge density. Charge density is what? Charge density is, what is the meaning of charge density? Charge per unit volume, na? Okay. See, listen. This is a small charge. Okay, the small charge dq with respect to a small amount of volume. Small charge with respect to a small amount of volume. Okay, and lambda is not a small amount. Lambda is not a derivative here. It is a constant. So I can write lambda as charge, that is the entire charge q, the entire charge of this Gaussian surface, which it's holding, upon 4 by 3 pi capital R cube into dV, that is the small volume which we have taken. Small volume is what? The Gaussian surface. Okay, dV is what? The small volume. Now considering the fact that the solid sphere, this red color sphere, entirely has a radius of capital R, and the Gaussian surface, okay, the Gaussian surface, which is green color, is having a radius of small r. It is having a radius of small r. So I can write dV, that is the volume, the dV, this is dV, this is the volume of the small sphere, the Gaussian sphere. Okay, I can write it as 4 by 3 pi small r cube, and I can write dr. Is this clear?
Yes, sir.
Yeah, you understood. If you didn't understand, I'll explain it again. You understood? Here what I'm doing, see here what I'm doing is basically I am telling the equation, I am telling this equation that, see, there is a charge dq, okay, and this dq is a small amount, is inside a small amount of volume, that is 4 by 3 pi small r cube. Am I right? There's a small amount of dq in a small amount of volume, and this 4 by 3 pi r cube is basically what? Volume of the Gaussian surface, which is small. Okay, but it is inside which? What? It is inside what? It's inside an entirely big solid sphere, and that solid sphere is basically what? Charge per unit the volume of the entire sphere, 4 by 3 pi capital R cube. You understood this? Okay, is this clear? So
Yes,
in this,
sir.
yeah,
Yes,
so
sir.
in this way, no, in this way, I am telling the equation that basically I'm using a sphere of Gaussian surface in an entirely bigger sphere. If suppose it was a disk, no, if suppose it was a disk, okay, just imagine the Gaussian sphere was a disk, okay, then here dV would have been what? The volume or the area of the disk. Okay, this dV would have been the volume or the area of the disk, and lambda would be this only, because we are trying to find out a electric field intensity at a point P due to this sphere. So this sphere is there. Gaussian surface, I can take anything. I want to take circle, I can take a disk, I can take anything. Only dV will change. dV is what? Small amount of volume. Okay, Gaussian surface is what? It's the charge which is Gaussian surface is the surface in which charge is enclosed, and so dq is that charge, the charge which is enclosed in what? It's enclosed in a particular volume. What is the shape of that volume? What is the area? What is the volume of this? That I have to mention here. So this Gaussian surface is small, 4 by 3, small pi r cube. Okay, this 4 by 3 I got cut, this pi I got cut, this 4 by 3 cut, this pi I got cut. What remains is q small r cube upon capital R cube. Is that clear?
Yes, sir.
Yeah. So I wrote q small r cube upon capital R cube into dr. So I got dq is equal to this. I will put this dq in this q charge enclosed. You understood this? I got na. I got what is q. So I can write q in that way. You understood? I'm going to do exactly that. I'm going to rub this. So now I know that I can write this q. Okay. Okay. I can write this q in what format? I can write it as capital Q small r cube upon capital R cube. Yes or no? Capital R cube into epsilon naught, which is here. Any doubt so far? No doubt, no? No doubt? If there is any doubt, please let me know. What is the area going to be? Area? What is the area going to be?
4 pi
4
r
pi
square.
r square.
Yeah, so it is going to be 4 pi. But which R?
Capital R.
Small r.
No.
Small
Small
r.
Smaller. Smaller. Why now? Why smaller? Arre, you are trying to find out the electric field intensity at this point P with the help of a Gaussian surface. So you will use the Gaussian surface radius. Understood? Any doubt?
Yes, sir.
Okay. Q R cube upon 4 R cube into epsilon naught. What gets cut? This R square gets cut and this R will get cut. Okay. What remains is E is equal to Q R upon 4 pi capital R cube epsilon naught, and this I can write it as what? 4 pi epsilon naught, I can write it as KQ small r upon R cube. Am I right?
Yes,
Yeah.
sir.
KQR upon R cube. So this is the electric field intensity at a point P inside a solid sphere. Don't make a mistake in a hollow sphere. Inside a hollow sphere, it is 0. Is it clear?
Yes, sir.
Okay.
Yes, sir.
Is there anyone who wants again an explanation? If at all, please let me know. There is no problem. So right now, we know one thing. That if I take a solid sphere, electric field intensity at a point outside will be what? KQ upon R square. And electric field inside is going to be what? E is equal to 0. This is E inside. And when I talk about a solid sphere, okay, then what is going to be E? E is again going to be, E at a point outside is going to be what? E is equal to KQ upon R square. Okay, KQ upon which R? It is going to be R square. And what is going to be inside? E inside will be what? Just now we derived E is equal to KQR upon R cube. These 4 equations, they are supposed to be by heart for you. There should not be any confusion. Okay. Now, when I say by heart, don't simply just by heart. Try to understand stuff. Okay. What happens if you make this R? Try to play with the equations. That's when you start understanding. If you reduce this R very badly, what is going to happen? Electric field intensity is going to increase. You understood? If you increase this charge, what is going to happen? Electric field will increase. K is constant. If you decrease this R, what is going to happen? This electric field will increase. Look at the diagram and try to understand. That is when you will start to learn things. Otherwise, there's no point. Don't try to understand stuff like this just for the sake of studies and giving exams, because that's okay. People outside are actually studying for their interest. We study for the job. Okay. So try to understand the subject more. Try to, develop an interest. Okay. That's enough of talking. So now electric field intensity due to an infinite cylinder. Let's take a cylinder. And this cylinder, okay, what is going to be the Gaussian surface for this cylinder?
Sir, smaller cylinder.
What is going to be the Gaussian surface? No answers.
Cylinder.
Yeah, it will be a
Cylinder.
cylinder. This is going to be the Gaussian surface. Now, considering that the distance of this from the axis, okay, from the axis, let me take it as capital R, and the distance from the axis to the end point here as small r. I want to find out the electric field intensity at this point. So I will take a small element. I know one thing, that the electric field intensity at this point is going to be like this. The field is going to be, E is going to be like this. And I know that the area vector will be like this. And considering the fact that this is a small element, I'm going to write dA. Okay. Now also remember one thing, that this is L. Okay. Now I know this much. That's enough. Now you all tell me, what is going to be the electric field intensity if I tell you to find out through this element over here? What is it going to become? It should be by heart for you.
0.
0.
Zero.
What is it going to become if I take it here, right here?
0.
0.
0. Why? Area vector is like this over here, area vector like this over here. I don't need to explain that now, I guess. So now I will directly go with the equation that phi is equal to Q upon, remember to write Q in upon epsilon naught. Q in upon epsilon naught. So what is it going to be now? How can I write phi as
EA.
EA? And what is A? What is A? What is A? Yesterday we saw.
Area
What
of
is
the
A?
cylinder.
2 pi RL.
Yeah.
2 pi RL.
Yes, right. Area of the cylinder, but area of the cylinder where only the outside surface, only the outside, the curved area is there, no? Only that we have to take, not the upper portion, not the down portion. So what we are going to do, we know that the circumference of this circle over here is going to be 2 pi r. If we multiply it with L, we are going to get only the curved surface. Okay, so I'm going to write phi as EA, and I'm going to write EA as E into 2 pi RL. 2 pi RL. Now, okay, it's going to be a small r. Because why small r now again? Because I am, EA means what? Phi means what? Phi is this entire equation is about the Gaussian surface. Okay, it's about the Gaussian surface. The cylinder, the Gaussian surface over here is basically this thing. Okay, this red thing, this red cylinder, and so the radius of this cylinder is smaller. So I'm mentioning smaller. No confusion should be there over there. Okay, and now charge enclosed, I can write it in terms of density. No, I can write it in terms of density again. Yes or no? I can write sigma. I can take lambda or sigma or whatever. Sigma is equal to charge enclosed upon area. Charge enclosed upon area.
Yes, sir.
Okay. So what is going to be the area now?
2 pi RL.
What is going? It's going to be pi r square L.
Fire.
Pi r square L. Who didn't get it? See, look here. Sigma is equal to charge upon area. Okay. Charge upon area of what? Where is the charge right now? Is it here? Is the charge here? No, na? Is the charge here? No. Where is it? It's inside this. It's this, na? It's on the surface of this. Yes or no? Yes or no? It's inside this. It's inside. It can be inside. It can be outside. It can be anywhere. So I am going to take area as sigma is equal to Q upon pi capital R square into length, because I am only considering this length. So I am only looking at this part. Is that clear?
Yes, sir.
Yeah, any doubt, please let me know. Sometimes it gets confusing to understand, but if you pay attention, no, if you try to understand stuff, you will understand it. See, sigma is equal to charge upon area. Where is the charge? Charge is not here over here. It's here in this green thing. Okay, it's going to be here. So we are bothered about this area. We're only bothered about this area. And so the area of that is pi r square. That is the area of the circle into the length. That will give you the entire area of this. And so ultimately what we are going, I can write this sigma, this charge q as sigma times pi r square L. Okay, sigma times pi r square L. I'll just substitute that. What I will get, I will get E. Okay, what I will get, sorry, 2 pi small r L equal to charge I can write as q into pi capital R square L upon epsilon naught. What is getting cut now? Pi gets cut. This pi got cut. This L got cut. L got cut. What remained is E is equal to sigma R square upon 2r epsilon naught. Am I right? 2r epsilon naught. So this is electric field intensity at a point P outside a cylinder, outside an infinite cylinder. Okay, you understood?
Yes, sir.
Only one is giving a response, no others are giving response. Now,
Sir.
yeah, okay. What is the electric field intensity? Say, suppose I have that same cylinder. I made it a little big now. I want to find out the electric field intensity at a point which is inside. What is going to be my Gaussian surface?
Cylinder inside.
They're
Yeah,
inside.
cylinder inside. Yeah. So I will draw a cylinder inside right here. Okay. Now, just the same thing. The earlier way, I had taken the entire the main infinite cylinder from here to here. I had taken the radius to be capital R. I will just do one thing. I will take the radius of this small Gaussian surface as small r. Okay. So now, if I know this much, that is enough. I can again tell you, if I take a small element over here, electric field intensity is going to be like this, and area is going to be this way. So cos theta is going to be 0. So I'm not considering that only. Okay, I'm not considering that only. So phi is equal to phi total. Phi total is equal to what? Charge enclosed upon epsilon naught. How much time we got? We got time. 3 minutes. Okay, we got 3 minutes. We'll try to derive this equation. It's not too much. So phi can be written as what? E A equal to, what is the entire charge enclosed? I can write it as, I have to write it in terms of what? Lambda, no? In terms of sigma. So I will write that. Okay. I know that lambda is equal to charge per unit what? Charge per unit area.
Area.
So yeah, charge per unit area. So Q upon, what is the area? Pi r. What is the area of this? Right now I will take which r? The small r, no?
Smaller.
Because I am only bothered about this now. And so I know, because Gaussian, see, always take charge into charge up when you're writing it in terms of this now. All it matters is what the Gaussian surface is covering. If the Gaussian surface is covering a small r, you will take a small r. The Gaussian surface covers this entire thing, you're going to take capital R. Is that clear?
Yes, sir.
So pi r square L, considering the fact that this is L. Okay. So now, if I
Sir,
can
why
write
we have area is pi r square L?
why we are taking pi area, no? What is the area of this going to be?
Sir, but volume of cylinder is pi r square L.
Sir, you are
Yeah.
writing the formula of volume.
Yeah, okay, yeah, right, okay, of course, yeah. But what I'm considering this to be not a hollow cylinder. It's not hollow, okay? It's not hollow. Is that clear now?
Yes,
Is
sir.
that clear? Okay, is that clear? Sorry, I made a small mistake. Okay, is that clear? Any doubts so far? Okay. So I can write Q as what? Lambda times pi r square L. Yes or no? Okay. So this lambda pi r square L, I can write it over there instead of EA. So I'm going to remove this. I'm going to write lambda pi r square L upon epsilon naught. Considering what is area of the Gaussian surface now? 2 pi r L. Am I right? No responses. Please respond.
Yes,
There's hardly any. Yeah?
Yes, sir.
So what are we going to ultimately get? This pi is going to get cut. This pi got cut. R and R got cut. L got cut. What remained is E is equal to lambda R upon 2 epsilon naught. E is equal to lambda R upon 2 epsilon naught. This is the electric field intensity at a point inside the cylinder. Okay.